Hello, curious to peoples. I went over to storage looking for a book, The Physics of Semiconductor Devices, which I found, and stuck inside of it is this handwritten pages of calculations I did, and this is like it's like 40 years ago, and it's to you from me, and I don't know who in the hell you is. I just don't remember. I don't remember this. But it's actually a good exercise because it is a customer requesting a specific device. So let's go through it. It's really a lot of fun. Okay, I have to put this in context or it's not going to make any sense at all. Back in the day, gallium arsenide, when we first started, was just a real niche, the market. It didn't make its debut in the world until the cell phones came along. But back in the day, customers would call up wanting a specific uh, electronic device. They wanted a space like an FET or an integrated the circuit or a diode or something, and they had uh, very unique applications they wanted to use. We didn't mass produce these things back then, so we just lived on this custom work. And what this handwritten note here says, which I don't remember, was a customer called and requested a switch design with a threshold voltage, the VTH, of minus the 3.5 volts and a maximum drain source, the current IDS, of 312 the milliamps per millimeter. Okay? So let's look at a drawing of what is a gallium arsenide MESFET. So it is a metal to semiconductor, the field effect transistors. Now, we didn't make MOSFETs in gallium arsenide because the gallium arsenide doesn't have a stable oxide layer, so we had to do it a different way. So this is a typical the MESFET from back in the day. So you bought the substrate, was semi-insulating, and with epitaxial reactor, you would grow a buffer layer, and then you would grow a lightly doped active the channel, and this would be like in the 10 to the 17th electrons per cubic centimeter range. Then you would grow a heavily doped the contact layer, which would be in the 10 to the 18th the range. Then on top of this, you would put some metals, so to make the source and the drain. I remember we used the nickel gold germanium, and then we would heat it up so it would diffuse in, and it would then allow electrons to get in and out with minimal resistance. Then you do a bunch of patterning and the photoresist and all that stuff, and you etch out a channel down to this active layer here, right? And you put on your gate. So this is a Schottky barrier, the gate, and ours, if I remember right, was a layer of titanium, layer of platinum, and then all of the rest of this was gold. So most of it was gold. A gold being because it's a good conductor and it doesn't oxidize. Okay, so based upon what the customer the wanted, we had a standard the process that we used to define these channels and stuff. So we needed to know what thickness and what doping level is this to accommodate the requirements. All right. So we get started by consulting the Bible. I just showed you that. The Physics of Semiconductor Devices by SMZ, Chapter 6. I wonder if they still use this book in school. It's wicked good. All right. So from that book, we got the one-dimensional, the Poisson equation for current density in semiconductors, which states a change in electric field with respect to distance y. Now, in the drawing I stole off the internet, they're using this distance as a. Our distance is y, because that's the way I did it, is equal to the change in the current, the density rho of y, divided by the permittivity epsilon of the semiconductor of the material. All right? So it looks like this. We also know from Maxwell's equations that the first derivative of the field with respect to the distance is equal to the second derivative of voltage with respect to distance. All right. So we can now use this with this, and we're starting to get an equation which deals with voltage. All right. In a semiconductor, the current density can be expressed as the electron, the charge, this is a constant, and the doping, the level. So now we're starting to get into some real things here. This is the doping level we're looking for. All right. So we put that in here. We integrate this twice, which even I can do that. We get this expression. So we have a relationship between the voltage, the thickness of the layer we're talking about, and the doping. The rest of these are constants. These are all constants. All right. So what we want to do now is look at some issues you have to deal with. Now, I assume this is true for all semiconductors, but it's certainly true for gallium arsenide. When you have a gate, the metal that's sitting on top, now this is not diffuse, it's just sitting on top of the gallium arsenide. So this is raw gallium arsenide, this surface here. And what it does is forms a potential here called the Schottky, the barrier, all right? And you have to account for that when you're doing these calculations. And the Schottky barrier for the gallium arsenide, as far as I know, is a constant, and it's about in our case, it's negative 0.8 volts. So we have to put that into our equation and account for that happening. So now we can calculate our threshold of voltage. So we solve here, and I chose a electron, the doping, the level of 1.5 times 10 to the 17th. That's a very reasonable number you would see in gallium arsenide MESFETs. All right, so we solve for Y, and we get, now the VTH came from the customer, right? They gave us that number that they wanted. They wanted a threshold voltage of 3.5. Here we had to account for our Schottky barrier, the voltage, and then we plugged in the rest of our numbers, and we get 200 nanometers. So that would be the thickness we would grow here on top of this buffer, the layer, at very low doping, 1.5 times 10 to the 17th, to give us the threshold voltage that we wanted. Okay, so now the customer also had one other issue in there they wanted. They wanted a maximum drain source to current of less than or equal to 312 milliamps per millimeter. All right, now to calculate that, we have to go back to our drawing and think about some other weird thing that happens in gallium arsenide. I assume it happens in other semiconductors. I'm sorry, I don't know anything about silicon, but it certainly happens in gallium arsenide. Because this surface is not passivated here, it doesn't have any stable oxide, like I said. There's all these weird states that are going on here. There's dangling gallium bonds and dangling arsenic bonds. And what they do is they actually trap electrons. So underneath this gate, they form a depletion the region. And you have to account for that when you're designing these active the layers. You have to account for that depletion the layer that's not there, because these electrons get squeezed through this little channel here as they go from source to drain, right? So, but we calculate that using the exact same equation here, but the voltage in this case is the Schottky barrier height for gallium arsenide, which we know to be about 0.8 volts. So now we solve for that again, and we get 87.5 nanometers. That's our depletion region. So we have to subtract that from what we grew. So now we only got 112.5 nanometers at 1.5 times 10 to the 17th, the doping the level. So this is how we're going to determine how much the current we can get out of this, the IDS, the maximum drain source, the voltage, right? So now we can calculate the current in the channel as this equation. So IDS is equal to the constant times what's called the saturated velocity and the electron, the sheet charge. The saturated velocity of an electron in gallium arsenide is about 1.1 times 10 to the 7th the centimeters per the second. The saturated velocity, excuse me, is a term that would say at a very, very high electric field, something like 5 kV, how fast can an electron get from one place to another. And the only reason we were ever able to make a living in this, and later on became uh, the source of the transmit receive in a cell phone, is because the saturated velocity of electron in gallium arsenide is much higher than silicon. If it wasn't for this fact here, we would have never gotten off the ground. So thank God for that. All right. So, and the electron, the sheet charge, is just given by the doping level times the distance, the thickness, and we already know what that is, and it's accounted for in our depletion, the region, right? So we have our constant here, we have our saturated, the velocity, we have our doping level, and this is our what's left of our thickness, accounting for after the depletion, the region. So we get an IDS of 297 the milliamps per millimeter, which is less than what the customer wanted. So wasn't that fun? Boy, this is bringing back some memories. Anyway, I'll see you later.